Okay, yes. I hope you can hear me. My name is Niklas. Yes, I'm a PhD student from TU Darmstadt, and thanks a lot for the invitation to this workshop. I think I will now cover robotic assembly from a different perspective compared to what we've seen before. And the talk will be about learning task and motion planning for robotic assembly discovery. So,
sharing this. You should probably share the other screen. Hopefully it should work.
okay, so in this video, I will show you the motivation for our work. So the results that I will be presenting today are the outcome of a great collaboration with the Department of Architecture at Technical University of Darmstadt. So what you can see here is that nowadays we build buildings to last hundreds of years, while they face economic obsolescence after 20 years. And when they face economic obsolescence nowadays, you can see what happens. So sometimes we destruct the buildings, which means that we turn the building components into trash. And I think it's kind of clear that we cannot continue this way. So therefore, what we are working towards is this vision of modular robotic architectural construction. And to realize this vision, we are building on three main components. So the idea is to use modular building blocks for construction, which should then be assembled by robots in the loop. And the core idea is that when we use modular building blocks, like we can construct buildings or shapes now for our current needs. However, if in 10 or 20 years we want to reassemble them into something else, we use the robots to disassemble it, and then we can reconfigure them. And I think at the core of this vision are, of course, task and motion planning methods that realize the interface between the building blocks and actually realizing the structure. To break it further down from a research point of view, the problem that we were tackling is this 3D robot assembly discovery, which is mainly about long horizon planning. So the task here is having to build arbitrary 3D structures given a set of building blocks. So the idea is that the target structure that we want to build can come, for instance, from the designer. Then we have a set of building blocks, and now we want to find a policy that optimally combines the blocks to fulfill the desired shape as good as possible. Additionally, we want to consider the robot in the loop and ensure structural stability throughout the whole process. So the special difficulty of this process is that we have a twofold combinatorial complexity of, on the one hand, we need to figure out, okay, where should each block go to, because we don't know how the finished assembly with all of the parts should look like. And on the other hand, we also have to come up with a feasible sequence of execution. So you might wonder, okay, one approach to this robot assembly discovery problem could be task and motion planning methods. They run a full model-based optimization. However, contrary to this robot assembly discovery, they typically require an explicitly pre-specified goal state. So you typically already know where all of the blocks should go. And despite the simplification, task and motion planning methods are computationally super expensive, especially if you increase the number of building blocks. So on the other end of the spectrum, we can leverage current progress in machine learning and especially in representation learning. So we can try to come up with more end-to-end learning approaches that directly map from a problem description to low-level actions that can be executed by the robot. And they are based on flexible graph-based representations. However, of course, we have to note that they are less interpretable compared to task and motion planning methods. Still, because those methods can be way more reactive and evaluated quicker, in our first work, we will actually focus on an end-to-end learning approach for robotic assembly discovery. So we want to solve this problem through learning, and in particular reinforcement learning. So we first have to design the MDP. And in this case, we have a state S that contains three sets. So the first part is the set of target nodes that are here visualized in yellow. And basically these nodes span the surface that you want to fill or that you want to construct. Then We have the set of unplaced units, so the blocks that are still available, and we have the set of blocks that are already placed in the scene. Now in this first work, we assume that we have a relative action space, so you can place the unused available blocks with respect to the blocks that have already been placed. And we also consider like 4 reorientation actions around the set axis. And so the difficulty that emerges here is that you have a time varying action space, because as you move available blocks to blocks that are inside of the construction, the dimensionality of your action space changes. And so our idea here was to use graph-based representations that are trained through model-free reinforcement learning. Maybe one other thing to note here is that this MDP formulation is on a very high level, so it's not on the level of the fine actions for inserting the task, but it's like really targeted to realize this long horizon planning. And using reinforcement learning, and in particular model-free Q-learning, also allows us that the planning agent can react to non-idealities of the other policies that actually perform the placing of the parts. So how do these function approximators, these graph neural networks look like that approximate this quality value for all of the state action pairs? So given this scene, we first convert it into a graph-based representation. So for every block that is available, we spawn a node for the shape. We also spawn a node and for the blocks that are already built. Given this graph-based representation, we use multi-head attention mechanism to exchange geometric information between the nodes. This will result in us ending up with an encoded version of the graph. And finally, because of the actions are all defined relative between the two nodes, we can use the features of the node that should be placed and compare it and combine it with the features of the blocks that is already placed in the scene. And that way we can compute the Q values for all of the available actions in the scene. And now we have this Q-learning objective, and this Q-learning objective basically lets us explore in these robot assembly discovery environments. And of course, this Q-learning algorithm then also refines this representation. And so the trick is, because in this graph-based representation, all of the operations are local, this representation can seamlessly generalize to building 2-sided structures, 4-sided structures, and also different number of building blocks. And as you can see in this video, because of this node-based representation, we can also here deal with more irregular building blocks. So this first method that I've presented you, it can resolve the inherent difficulties of robot assembly discovery, it can realize long horizon planning, and most importantly, it's invariant to problem size. Moreover, it can generalize with respect to building blocks and target shapes. However, if we look at our evaluation, we have seen that, of course, the further you go away from the environments where you train this model, the failure rate can increase drastically. So the generalization obviously has limits. And therefore we went back and thought, okay, like how can we improve the results and how can we make this policy more generalizable? And I think for one, of course, we can try to do longer training and maybe use curriculum methods to tackle the combinatorial complexity with the increasing task horizon. Or the other idea is to add more structure, so to add inductive biases into the approach. And we actually decided for the latter. So in a follow-up work, we developed a method that tries to combine the best of model-based optimization and learning, which we called graph-based reinforcement learning meets mixed integer programs. So the follow-up approach is a hierarchical approach that tries to decouple the complexities of the problem that we are facing. So on the highest level, we run a mixed integer program that tries to solve the resource assignment. So which block type should go where. However, the highest level, so this mixed integer optimization doesn't consider the constraints that the robot is in the loop and that the structure should be stable, for instance. For these additional constraints on the intermediate level, we have again this graph-based reinforcement learning framework that is similar to the one that I've presented you before. However, now this graph-based reinforcement learning framework benefits from the higher level in that it doesn't need to explore all of the action space, but you can focus it on the outcome of the mixed integer optimization. And on the lowest level, we again run a classic cross motion planning algorithm. And again, also because on the intermediate level, we have this learned representation, it can adapt to potential non-idealities of this grasp and motion planning pipeline. So let me quickly walk you through the 3 levels of hierarchy. So on the highest level, mixed integer program, we don't consider structural stability, robotic feasibility, and task sequencing. So this is purely geometric. So we convert this scene into such a representation, a grid-like representation, where the objective is here C transpose times M times D. So C is a cost vector that incentivizes filling the pink voxels that should be filled throughout the assembly, while it penalizes unnecessary filling of the green voxels. Then this matrix M basically encodes how the grid state changes if you place the available blocks at different locations. And finally, D are the decision variables that you want to optimize for. And once you run this optimization as output, the mixed integer optimization tells you, okay, which block type should go where. But now, of course, to solve this task completely, we also need to consider structural stability, robotic feasibility, and task sequencing. And to capture these complexities, we again leverage this graph-based reinforcement learning framework, where as before, the input scene is transformed into this graph-based representation. Then we perform this message passing to obtain an encoded version of the graph. And now, importantly, for this Q-learning framework, we do now not evaluate the quality of all of the available actions, but now we only look at the actions that are actually proposed by the mixed integer optimization. Therefore, this mixed integer optimization effectively helps to guide the exploration of the reinforcement learning agent, and the reinforcement learning agent benefits the higher level because it takes away some complexity from the mixed integer optimization. So now let's look at the evaluation. So the first question that we ask ourselves is, okay, now we have this mixed integer optimization on top of the RL learning agent. So is this actually effective or not? So here we compare the 2 end-to-end approaches without the mixed integer optimization against the proposed hierarchical approach. And as you can see, across training and testing environments, the hierarchical approach outperforms the end-to-end one. And now the second question that arises, someone could say, okay, now you have this mixed integer optimization, maybe it already handles all of the complexity that arises in this task. So therefore we now design a heuristic that randomly picks from the stable placing actions that are proposed from the mixed integer program and compare this again to our proposed approaches. And as you can see, this learned intermediate level is again needed and significantly outperforms this heuristic. So this we can also see in image form, where here you can see the task sequencing using the heuristic, which because of the tight space where you need to place the blocks results in many collisions. And on the right hand side, yeah, you can see the performance of our proposed approach. Maybe one thing to point out is that here you additionally see MCTS on the right hand side. So we can use this learned Q function from the intermediate level to effectively do some model-based search on top, similar as the AlphaGo papers, to again increase robustness and performance of the overall approach. And last but not least, we can of course also evaluate and run this pipeline on the real robot. So the takeaway message from this follow-up work was again, okay, it can solve and handle this robot assembly discovery problem. It's again invariant to problem size, and we found that it exhibited better generalization compared to the prior approach. However, of course, one of the limitations, or one aspect that we didn't tackle so far in this talk, is we didn't consider any fine adaptive low-level picking and placing policies. So in the last part of the talk, I will now want to give an outlook on this towards robotic assembly with interlocking SL blocks. So the idea is that here we now use a different set of blocks, so not these rectilinear blocks, but SL blocks. And the cool thing about these SL blocks is they are interlocking blocks. So if you combine them together, all of the degrees of freedom, apart from the insertion direction, are locked with each other. And exploiting this interlocking property, actually a colleague from the Department of Architecture was able to manually build this branching column, which is built solely from tri-joint connections. So this means you can build such a column, and because all of the connections are tri-joint, after you don't need it anymore, you can basically disassemble it into the, I think it's around like 1000 SL blocks, and then you can maybe assemble them to build something else. Now, the price that comes with this very tight interlocking is, of course, that you need very dexterous skills to actually put the blocks together, as you can see here in this video of a master's student trying to do the task. So if we want to automate this, we thought, okay, we definitely need tactile sensing to react, for instance, to the blocks jamming with each other. So therefore, to go towards robotic assembly of these SL blocks, the first step was to equip the gripper with visual tactile sensors. And so here we actually put 2-digit sensors in the parallel gripper. And I mean, here you can see how the image changes if the block moves inside of the gripper. Then for the approach, to solve this task, we actually also started with real-world data collection through this keyboard interface. So the student was collecting good demonstration data. And in addition to this, we did a replay of the demonstration to get additional data. And during the replay, we perturbed the demonstration. The idea of gathering this data was to subsequently learn a model. Like back in 2022, I think like diffusion policies were not there yet. So we thought it would be a good idea to actually learn a transition model of this process. So we took all of the data that we have. So as the input, you get the tactile images, the current gripper pose, the current block pose, which is estimated from our Rupa markers, as well as the actions that come from the teleoperation interface. Then you try to learn this transition model to get the next gripper pose, the next block pose, and we also predicted the next latent for the tactile images in order to regularize the learning a better representation from the tactile images. And once you're done finishing this transition model, of course you can do it to generate actions through model predictive control. And here you can now see the autonomous execution of like this insertion policy. And here's a successful example. Like sometimes it got jammed too much and then it was unsuccessful. So the success rate here was about 65%. With this, I want to conclude my results, my talk. So we have shown that graph-based representations are effective for learning long horizon assembly tasks, and that leveraging classical optimization as priors for guiding or informing the RL agents yields performance improvements. And on top of this, we've also presented precise insertion policies leveraging visual tactile sensors. However, several challenges remain, and they are mainly focused on assembly in the context of construction. So for fully autonomous assembly for construction, I think we need further advances in robotic hardware. Like most of our arms are not powerful enough to actually deal with like larger real-world blocks. And I also think that, so the tactile sensors that we are using at the moment, they are also quite limited to rather light blocks. In addition, I mean, we've seen several great talks today, so I think maybe the problem of simulation is not that much of an issue anymore, but I think like once we really start to do assembly on a larger scale, so if you really want to connect maybe like 10 or 20 blocks together, then simulation might still be challenging and complicated. However, I also do think that learning in simulation and then trying to do like zero-shot transfer to the real world, I think it's very valuable. I think we cannot teleoperate all of the assembly tasks that we face. And lastly, of course, I think it would be very nice to have like a general kind of like insertion policies where you can give as input like the part that you want to insert and the placing location where it should go. And then you have like one policy to insert them all, as we've also already seen in a previous talk. So with this, I want to thank all of the collaborators who were involved in these research projects. And thanks a lot for your attention, and I'm happy to take questions.